In this presentation, we're going to take a look at AVEVA ERM and the role it plays in our integrated shipbuilding solution. This is a process that provides digital integration between the different shipbuilding disciplines, fostering collaboration that, through the changes that occur, maintains the project on a path to maturity. The purpose of this presentation is to introduce AVEVA ERM to a wider shipyard team and will focus less on the typical engineering activities. However, the concept of integrated shipbuilding will still be a common theme throughout. We'll see that integration and collaboration is a key strategy of the whole process. We'll use tailored digital communication between disciplines to ensure that information is shared in an expected and standard format. This information can be validated, exposing inconsistencies and mistakes that can later be highlighted for correction. As a continuous process, this ensures that those working on the project will achieve earlier maturity than if left to isolated documents, manual handovers, and meetings. This process involves many deep technical activities delivered by the shipbuilding experts. Therefore, to make it interesting, we're just going to focus on a pipe and its journey from engineering through to installation, and all the activities that need to take place to make it happen. First, we'll take a look at the reasons behind integrated shipbuilding and the role it can play in achieving project maturity. Shipbuilding is unique, especially for AVEVA, because out of all the other markets we deal with, it's one of the few that take responsibility for the whole project and product from inception to delivery. We see that shipbuilding is process driven, for without this we'd never deliver the complex engineering projects we start. It's driven by people, because they have the fundamental knowledge and experience needed to compose all the required systems together in a way that can be efficiently manufactured and safely operated and maintained. It's a complex process to navigate, it's certainly not linear, and there are a lot of decisions to be made based on the understanding of what's needed. And we cannot deny that the bottom line is where we are held to deliver on time and on budget. For all its technology, the integrated shipbuilding solution puts people at the core of the process to ensure effective communication. For without communication, we don't know what's going on. Individually, none of us have complete knowledge of how to build a ship, and we rely on the combined experience of our skills to resolve these challenges on the way. As a software solution, integrated shipbuilding supports the process by supporting the digital exchange of project data between the ERP processes and engineering. It synchronizes status information so that different disciplines are informed of the current state of the project. Consequently, status can be used to drive the decision-making process. Status can be used to control the path of the project. This focuses the project to work through towards maturity by the fact that everyone is now more informed in the decision-making process. Let's now turn to AVEVA ERM to focus on the specific activities this solution supports. AVEVA ERM focuses on all of the traditional ERP activities from project management, planning, production control, management of materials, purchasing, and stores management. It has four main focuses: catalogue management, where common materials and part specifications are managed; materials management, which procure all that is needed and tracks delivery through to the warehouse; planning organises the activities, collects materials from the warehouse and sets up job and processes to track the progress of the project; production allocates and executes jobs, reporting back up to the planning process. When you get into the detail, the solution is quite complex. I had my first proper introduction to ERM back in 2015, where a team of colleagues were introducing the solution to a shipyard that I was delivering training at. It was a big conference meeting over 5 days. There is some deep content here, but when you get down to the individual roles in the process, it's not too complicated. It's all about, when do I need it? When will I get it? Or do I already have it? So rather than spend 5 days, we've distilled the whole process down to 25 minutes. We're going to focus on a typical pipe engineering and fabrication scenario and track it through from design into installation. We'll start by seeing the engineering process, where the designer will first start preparing the functional design information. With assistance from the software validation process, they'll introduce the information needed for fabrication. Then they'll produce the manufacturing outputs and communicate the bill of materials information to AVEVA ERM to the materials management team. The material management team will review this information and accept it into the planned activity. Then they'll requisition the material needed to deliver the activity. This will pass the initiative over to Procurement, who will, in our example, prepare an RFQ. This will subsequently be reviewed by a supplier who will return a quote. Procurement will follow up on this, preparing a purchase order and preparing the delivery tracking information. This entire process will happen digitally. Following this, we'll hand over to detailed planning, who will generate the individual jobs required to execute the activity, requisition materials and parts from the store before issuing the detailed plan. Finally, we'll see the role of the supervisor issuing and tracking the individual jobs and how this information is rolled up to the detailed plan and to the project plan. To note before we begin, the videos together make up 25 minutes of content. The original content my colleagues recorded lasted 45 minutes, so like the Apple adverts, these sequences have been shortened for clarity. But it's worth pointing out the activities you'll see will probably take place over days, weeks and months, so in this respect the shortening is keeping things to the point and interesting. So we'll start with the engineer. They'll be designing a pipe, validating the engineering, subsequently producing the production information, and then issuing the bill of materials. Let's begin in the 3D environment, in the engine room. We have displayed here a machinery space with 3 generators and the lube oil system to the right. We're going to be connecting the system up to the genset on the far left and to the pipe branches already placed for the other gensets in between. We'll start by creating a pipe, naming it, and selecting a specification that will dictate the components and standards we're allowed to use. Then we'll define the intended bore size and some of the operating characteristics. Next we'll establish the start and end of the pipe, termed the head and tail. This involves interactively selecting the intelligent nozzles to define an indicative pipe trace presented at a straight, lotted line. We'll be connecting the filter to the far genset. Next, using the menu, we'll add and position components. This is one of the many ways of building up a pipe. The position and orientation of pipe components are constrained to behave as a pipe would in the real world, as you'd expect. This simplifies the designer's actions during the preparation of this information. Swapping to the other end of the pipe, we'll add a gate valve and place it in a clash-free position with respect to operation and maintenance considerations. The software will ask us to select additional components, in this case the subsequent flange specification required following the valve in the sequence. We'll now move on to the completion of the pipe to allow us to focus on consistency and fabrication. Using the alignment tools, we'll place the final set of bends and elbows to connect the pipe from head to tail. Note that designer has never touched the tube itself, it's implied between the piping components looking after itself. With the pipe complete, we'll now run automatic consistency checks to validate if the design conforms to the level of information required to proceed to fabrication. The data consistency check is a first level of maturity after design. The data consistency check in this case reveals 4 violations, 3 incomplete connection references, and a bend that falls outside the capability of the bending machines. The designer will now update the pipe to conform to the standards led by the output of the consistency check. We'll run a final check to confirm an acceptable design. Next, we'll perform a fabrication check. This will confirm that a pipe can be built within the facilities, processes and standards used in our production process. Fabrication check highlights an invalid section with 2 violations where the requested tubing is both longer than the stock length and longer than the capability of the bending machine. Since the pipe has yet to be split into spools, this is the next logical step. The pipe splitting process is automated, determined by a number of rules. In this case, we will specify a minimum and maximum spool length. We will also need to select the specification for the splitting flanges. After selecting the portion of the pipes we want to affect, the additional pipe components required to define the spools are introduced into the sequence. The pipe will now pass the fabrication checks, which allows this data to be released for fabrication. This state will allow us to generate the associated drawings. We'll start with the individual spool sketches. Next, we'll generate the overall piping isometric. You'll note that the isometric contains parts and bolting lists retrieved from the catalogue. The designer never directly specifies this information, and this demonstrates yard standards being brought through into the production outputs with automatic consistency. At this stage, we've completed the engineering tasks and will hand over leadership to the planning, procurement and material management in ERM. To communicate these intentions, we'll raise the status on the pipe, which will mark it to allow us to publish the part list information to planning and procurement. This process may also introduce a lock on the pipe to prevent unauthorized modifications until the required change management workflow steps have been followed, but only if this is a desired implication of your maturity management strategy. Next, we'll publish the information that has changed state to ERM as we hand over to that stage of the process. No need to create paperwork, leave your chair, or even have a conversation. So we saw the engineer designing the pipe. He followed up by validating the design using the data consistency and the fabrication checks. Once complete, he issued the manufacturing information in terms of the spool sketches and the isometrics. Following that, they issued the bill of material. One should note the interactive creation of the functional design content, how production design was supported by validation checks, and the automatic outputs supported by catalogue and standard information. We were able to capture maturity using status, and we issued the new bill of materials digitally. We'll now move on to the project planning process. In handing over the bill of materials, the project planner will review the activity with respect to that information. They'll update the project plan, review the material balance, and request any material that's needed. Now in ERM we can see we've received a part list, and this is allocated to an activity, Pipe 004 403 0101, which we'll shortly see in the project plan. In this state, the received part list is pending review and release into the plan. The part list contains all the items just issued by engineering. These items will automatically inherit dates when they were acquired by virtue of their association with the activity. In the project view, a Gantt chart will scroll through to the activity, and you'll note it's highlighted by a black dot in the material state column. Action is required. Selecting the activity, a black material status against each part in the material list indicates it's unavailable. Having checked the parts list, we'll now issue it into the planning process. Now taking a look at the material balance, we see here a selection of red arrows, indicating that there's no stock of any of the items in the parts list. The graphical timeline of material balance, which indicates inventory and utilization of resources in the project, is negative. To address this, we'll turn this demand into a technical material request, a TMR, and issue it to Procurement to obtain the materials we need. The TMR is generated directly from the stock request. In addition, we can attach the associated engineering documents seen previously to support the business process as we go out to third-party suppliers. Documents can be attached as a pack, zipped, or individually. We'll give the TMR an identifying title, check and review the header, then issue for approval. Returning to the material status, once the TMR has been issued, the material status is now non-negative. So we saw there the role of the project planner once they received the bill of material information. They reviewed it, updated the project plan, and for any material that was outstanding, reviewed the material balance and issued a request for additional material. It's interesting to note that these spools have been received as fabricates. We'll be issuing them to a third-party supplier. An alternative is that we could be generating these spools from fabrication using standard material. It's a very similar process that works in parallel to what we've been showing. We'll now be looking at the procurement process. Based on the material request we just issued, Procurement will issue an RFQ, and they'll issue it into the Supplier Portal. The supplier then has the opportunity to review the RFQ and prepare a quote accordingly. Back in Procurement, they can review the quotes, select which one they want to move forward with, issue a purchase order, and prepare the delivery receipt for any parts and materials coming into our warehouse. The initiative now falls on Procurement to acquire the parts we've just requested. They'll find the TMR in an effective inbox, the buyer queue. We'll turn the TMR into an RFQ, which in this case we'll publish to the Supplier Portal. All of the requirement dates are carried through based on the activity the parts were associated with. We can set the relevant dates over which the request is valid and any other characteristics. Here we are selecting the suppliers we'd like to quote on this RFQ. Attachments added to the TMR are automatically carried through into the RFQ. Submitting the RFQ highlights the chain of approval. This workflow can be tailored for each organisation, with separate individuals holding responsibility to fully issue, for example, RFQ and purchase orders. You'll see that process happening several times in this session. Now we turn to an external view of this data. The Supplier Portal is where third parties can electronically respond to your RFQs, managing all the information exchanged in one place within a qualified workflow. The RFQ dashboard shows the state of all the RFQs, and we can see that we have one available to process. Going into it, we see a mirror of the information we prepared in the RFQ and can view the documents attached in the previous step. To complete the document, mandatory fields are highlighted. Relevant business terms can be set, or the form can respect previously agreed framework agreements. In this case, we'll manually set the quantity and price of the parts requested. The supplier can also attach any digital document that are relevant to the quote or to parts of interest. The supplier will now finalise the form and mark it as complete. Exiting the form, the status will then be reflected in the RFQ dashboard. Back in the procurement department, we'll receive the follow-up and all of the information submitted by the supplier, terms, prices and dates. If multiple suppliers have been selected, their submitted information can be compared between each other. We also have access to any documents the suppliers may have attached. To assist supplier selection, there are facilities to highlight the RFQ with the lowest price and expose any information supplied that does not meet the expectations of the original request, in this case quantities not being met. To proceed, we'll generate a purchase order from the selected RFQ. The purchase order already contains the information from the RFQ and will add information such as the relevant account classifications. You'll note that as we've been going through these processes, mandatory information has been highlighted in yellow to assist the user correctly complete forms that are often quite visually busy. The purchase order is issued into an approval process where subsequent roles can confirm if it can proceed through to action. At this stage, the role of procurement is mostly done. We now need to raise information to notify and capture deliveries as suppliers complete their side of their purchase orders. Delivery registration will capture individual consignments if separate, allow for review and acceptance of delivered items as part of a quality control process, and capture where in storage these items will be held until needed. Completion of the delivery registration will capture what has actually been delivered compared to what was requested, and update the actual material balance feeding into the planning process. Let's return for a moment to the planning process. The material status on this activity will now show green. We're good to go ahead and prepare the detailed plan for this activity. So there we saw the procurement process. The procurement team issued RFQs that were processed in the Supplier Portal. Subsequently, they reviewed quotes, issued a purchase order, and prepared the delivery receipts. We note that this was a fully tracked, digitised activity including the exchange of documents. In this case, we've gone out to a third-party supplier to deliver the spools as effectively parts. But we could have done this through an internal manufacturing process, and the equivalent sort of procurement processes in that, in terms of buying standard materials, would be what we would have seen in this case. We'll now move on to detailed planning. In preparing the planning activity, the detailed planner is going to be allocating the parts list to the range of jobs that will generate throughout this process. We'll then have to requisition material from the store to tag those parts with the activity and mark them as being used. The detailed planning process takes advantage of a templatization process. This is where a generic set of jobs that are targeted at an activity are combined with a bill of materials and parameters by the norms and complexity to generate an outline plan for each range of tasks that we need for fabrication. The outline plan can then be updated with the specifics based on the planner's detailed knowledge of how things should be progressed. The detailed plan first needs to be aware of the resources that will be used in the activity. Here we are finalising the assignment of 2 departments to the activity with their respective budgets. Following this, we can generate the detailed plan. The initial detail plan contains each task, its duration, but it is not yet sequenced. It also doesn't have any material. Updating the material status, we can see the sequence of black dots just like we saw with the initial part lists when imported. Like then, these indicate that we have yet to assign any material to the task. Also indicated are 2 delivery requests, DRLs, which prompt collection of any required material and parts from the store, allocating it to these tasks. Completing the DRL confirms this request. It could be used to prompt a picking activity in the warehouse depending on the degree of automation required. Once completed, the status indicates that material is now confirmed as allocated to this activity. Moving on, digging into the task, we can see that individual parts in the activity are confirmed as available. Next, we'll schedule the plan which will sequence it with respect to the prerequisites. The details of the schedule may be manually adjusted and regenerated again if necessary. Finally, we may of course include any manufacturing information associated with the activity, and we'll attach the isometrics in this case which you saw generated earlier. Detailed planning is now complete, and we'll roll up and release each section of the plan in turn, starting with the activity in the project view and then with the detailed plan. So we saw there the detailed planner planning the activity using a templatization process, allocating parts to the activity to the respective jobs, and setting up the requisition process to extract the parts needed from the stores. We note the use of templatization to turn an activity into a range of individual jobs. The number of jobs and the time that they take is parameterized by the use of norms and production performance statistics. Next, we'll look at the role of the supervisor. The supervisor is going to be allocating jobs to specific resources, and as the job progresses, we'll be capturing back reporting information. That information will be progressed onto the detailed plan and subsequently can be visualized in the overall project planner. Now that the detailed plan has been released, we'll create the individual jobs and capture progression through a back reporting process. Here we are defining the first job in the activities detailed plan to pick up the required parts from storage. Required paperwork can be automatically generated stating the details of the job and any parts required. Barcoding can be used to feed into a digital tracking process. Now that the job has been started, we can collect information on progress. Reporting back will capture hours spent and the degree of progress made. The job is now completed, and the record itself will capture start and finish dates as well as the actual time used to complete the task. This information will roll up into the detailed planning information, And on to the project view plan. So there we saw the role of the supervisor. They allocated the job to resources, and as the job progressed, captured information to report back into the overall planning process. We note the seamless integration of this information into the project process and plan, and the way that automatic deliverables like job cards were generated from the system. We also note that there's opportunity to bring mobility into the working environment. So drawing the presentation to a close, we've seen how integrated shipbuilding supports the engineering, planning and procurement and fabrication disciplines in the preparation of information required for production, by providing both a tailored means of communicating information and tracking maturity. These two factors provide a baseline to understand progress and allow each discipline to identify and address inconsistencies. Subsequently, we introduced AVEVA ERM, which delivers materials management, planning and procurement capability. Since this solution provides so much capability that only really the experts in these fields will want to dig deeper, we used a pipe fabrication scenario to tell the high-level story of the information journey from engineering through to the workforce. This gave us the opportunity to demonstrate the integrated transfer of information and workflow throughout the whole process, demonstrate the ability for the software to validate information exposing inconsistencies, to show how ERM can address different fabrication opportunities using standard material when building in-house or fabricates when outsourcing. And when it came to detailed planning, we introduced how templatization is used to reduce planning hours by generating this information from standardized tasks and parameterizing them by shipyard norms and complexity factors. The presentation is now complete. I thank you for your attention and welcome you to contact AVEVA for further information.